Welcome to a new session on the massive open online course Introductory Concepts of Digital Computing offered by Swayam. In the last few sessions, we were discussing on various combinational circuits. Here, I would like to introduce another important combinational logic circuit, multiplexer. In the first part of this session, you will be taught what a multiplexer is. The difference between multiplexers and multiplexing and different types of multiplexers will be discussed in the next part. What is a multiplexer? The multiplexer or MUX is a digital switch. It is also called as data selector. It is a combinational logic circuit with more than one input line, one output line and more than one select line. Multiplexer accepts binary information from several input lines or sources, and then depending on a set of select lines, a particular input line is routed onto a single output line, and so they are also called as many to one combinational circuits. Look at the block diagram of a multiplexer shown here. It consists of n input lines, m selection lines and one output line. For m selection lines, the number of possible input lines is 2 raised to m. Alternatively, we can say that if the number of input lines is equal to n, that is 2 raised to m, then m selection lines are required to select one of n input lines. For example, if a multiplexer has 4 input lines, how do we select a particular one? The select lines must produce a value between 0 and 3, and according to this value, one input line should be selected. To produce a value between 0 and 3, how many bits are required? 2 bits. So, if it has 2 select lines, 4 input signals can be used. In general, for m select lines, a multiplexer can have 2 raised to m input signals. This type of multiplexer is referred to as 2 raised to m by 1 multiplexer or 2 raised to m to 1 multiplexer. For example, if the number of input lines are 4, we write 4 by 1 multiplexer. Then for 8 input lines, it is 8 by 1 multiplexer. Generally, the number of data inputs to a multiplexer is a power of 2. Some of the most frequently used multiplexers are 2 to 1, 4 to 1, 8 to 1 and 16 to 1 multiplexers. So, we understood that in a multiplexer, data are switched from several lines to a single line. Thus, we can define a multiplexer as a device that allows digital information from several sources to be routed onto a single line for transmission over that line to a common destination. The basic multiplexer has data select inputs that permits digital data on any one of the inputs to be switched to the output line. Now, let us know what is multiplexing. What is multiplexing? It is the process of combining one or more signals and then transmitting it on a single channel. There are different types of multiplexing such as time division multiplexing, frequency division multiplexing, space division multiplexing and a few more. For transmitting digital signals, time division multiplexing is commonly used. Landline telephone network and cable TV are the best two examples of multiplexing systems used in our day-to-day life. In the example of cable TV, multiple channels or multiple information streams are sent to a common cable to a user's place. That is multiplexing. The device which performs multiplexing is known as multiplexer. Multiplexers can be used for both analog and digital signals, but let us focus on digital signals. It is an important building block in many of digital systems, and they are found in many applications such as data selection and data routing, logic function generators, digital counters having multiplexed displays, telephone network, waveform generators, etc. It is particularly used in communication systems for the efficient and cost effective use of a communication channel, because it allows multiple users to share a single channel in a logical way. This session is planned to discuss about different types of multiplexers and its logical design. Let us see how different types of multiplexers are implemented. From logic gates, we start from a 2 by 1 multiplexer. 2 by 1 multiplexer. A 2 by 1 multiplexer consists of two data inputs D0 and D1, one select input S and one output Y. Since there are two input signals, only two ways are possible to connect the inputs to the outputs. So, one select line is adequate to do the operations. Depending on the select signal, the output is generated from either of the inputs. If the select line is low, that is S equal to 0, then the output will be switched to D0 input. Whereas, if select line is high, that is S equal to 1, then the output line will be switched to D1 input. Block diagram of a 2 to 1 multiplexer is shown here. Notice the enable input signal E in the block diagram. It is to control the multiplexer. It makes the circuit enabled or disabled, depends on the value of E. Look at the truth table of 2 by 1 multiplexer. Depends on the value of the select input, the output is produced. The value of S decides which data line to be connected to output. If S equal to 0, value of D0 and S equal to 1, value of D1 is at the output. Refer the truth table. When S equal to 0 and D0 equal to 0, the output is 0, and when S equal to 0 and D0 equal to 1, the output is 1. See the next two rows. When S equal to 1, the value of D1, it may be 0 or 1, is at the output. You know that the X in this truth table denotes a don't care condition. After ignoring the don't care conditions, we can derive the logical expression of 2 by 1 multiplexer as Y equal to S D0 plus S D1. We have already learned how to derive Boolean expression from truth table in the previous classes. You may just review those topics if necessary. Okay. From the expression Y equal to S D0 plus S D1, which is the output expression, the logic circuit of 2 to 1 multiplexer can be implemented. It consists of two AND gates, one NOT gate and one OR gate. When the select line S equal to 0, the output of the lower AND gate becomes 0, but the output of the upper AND gate generates D0. Thus, the output generated by OR gate is equal to D0. Similarly, when S equal to 1, the output of the upper AND gate becomes 0, but output of lower AND gate generates D1. Therefore, the output of the OR gate will be D1. Thus, the above given Boolean expression is satisfied by this circuit. 4 to 1 multiplexer. The next we discuss a 4 to 1 multiplexer. What is a 4 to 1 multiplexer? It has 4 input bits, 2 control bits and 1 output bit. The 4 input bits are D0, D1, D2 and D3. Only one of this is transmitted to the output Y. The output depends on the value of S1 and S2, which are the control inputs or select lines. However, the control input determines which of the input data bit is transmitted to the output. For instance, as shown in figure, when S1, S2 equal to 0, 0, the upper AND gate is enabled while all other AND gates are disabled. Therefore, data bit D0 is transmitted to the output, giving Y equal to D0. If the control input or select input is changed to S1, S2, that is equal to 1, 1, all gates are disabled except the bottom AND gate. In this case, D3 is transmitted to the output and Y becomes D3. We will write the truth table more conveniently as given here. The S1, S2, Y values are given 0, 0, y is d naught, for 0 1 y is d1, for 1 0 it is d2 and for 1 1 it is d3. How to develop a logical expression for this circuit? Here y equal to d naught if and only if S1 equal to 0 and S2 equal to 0. That is y equal to S1 complement S2 complement d naught. When S1 equal to 0, S1 complement will be 1. When S2 equal to 0, S2 complement will be 1, and these lines are connected to an AND gate with d naught input. So, when S1 equal to 0 and S2 equal to 0, that particular AND gate produces a signal d naught and all other gates produces 0 value. Similarly, we can generate the expressions for each separate output. Y equal to d1 if and only if S1 equal to 0 and S2 equal to 1. That is y equal to S1 complement S2 d1. Then y equal to d2 if S1 equal to 1 and S2 equal to 0. Then y equal to S1 S2 complement d2. And finally, y equal to d3 if S1 equal to 1 and S2 equal to 1. Then the expression becomes y equal to S1 S2 d3. Thus, by adding all these, we get the final expression as given below: y equal to S1 complement S2 complement d naught plus S1 complement S2 d1 plus S1 S2 complement d2 plus S1 S2 d3. 8 by 1 multiplexer. The next we discuss an 8 by 1 multiplexer. As we already discussed two lower order multiplexers, this is more easy for you to understand. The 8 to 1 multiplexer has 8 input bits, 3 control bits and 1 output bit. The 8 input bits are D0, D1, D2 etc. D8. Only one of this is transmitted to the output Y. The output depends on the value of S0, S1 and S2, which are the control inputs or select lines. The truth table given here clearly explains the function of 8 to 1 multiplexer. The logical expression can be derived from the truth table as y equal to S1 complement S2 complement S3 complement D0 plus S1 complement S2 complement S3 D1 plus S1 complement S2 S3 complement D2 plus S1 S2 complement S3 complement D3 plus S1 S2 complement S3 complement D4 plus S1 S2 complement S3 D5 plus S1 complement S2 complement S3 D6 plus S1 S2 S3 D7. This is the circuit diagram of 8 to 1 multiplexer designed from the expression Y. Higher order multiplexers. There are a large number of higher order multiplexers. You may have a curiosity to know how these higher order multiplexers are implemented using lower order multiplexers. Think for a moment. How an 8 by 1 multiplexer is implemented using 4 by 1 multiplexers and 2 by 1 multiplexer? It is done in two phases. We know that 4 by 1 multiplexer has 4 data inputs, 2 selection lines and 1 output, whereas 8 by 1 multiplexer has 8 data inputs, 3 selection lines and 1 output. So, we require 2 4 by 1 multiplexers in first phase in order to get the 8 data inputs. Since each 4 by 1 multiplexer produces 1 output, we require a 2 by 1 multiplexer in second phase by considering the outputs of first phase as inputs and to produce the final output. 8 to 1 mux using 4 to 1 mux. The logical diagram of an 8 by 1 multiplexer using 4 by 1 mux and 2 by 1 mux is given here. 16 to 1 multiplexer. After 4 by 1 and 8 by 1 multiplexers, we can go to 16 by 1 multiplexer. In the 16 by 1 multiplexer, there are total of 16 inputs D0, D1, D2 etc. D15. Then 4 selection lines S0, S1, S2 and S3 and a single output Y. On the basis of the combination of inputs that are present at the selection lines S0, S1, S2 and S3, one of these 16 inputs will be connected to the output. The truth table, logic diagram and Boolean expression are shown here for your reference. The logical expression is given here, y equal to d naught S0 complement S1 complement S2 complement S3 complement plus d1 S0 complement S1 complement S2 complement S3 plus d2 S0 complement S1 complement S2 S3 complement plus d3 S0 complement S1 complement S2 S3 plus d4 S0 complement S1 S2 complement S3 complement plus d5 S0 complement S1 S2 complement S3 plus d6 S1 S2 S3 complement plus d7 S0 complement S1 S2 S3 plus d8 S0 S1 complement S2 complement S3 complement plus d9 S0 S1 complement S2 complement S3 plus d10 S0 S1 complement S2 S3 complement plus d11 S0 S1 complement S2 S3 plus d12 S0 S1 S2 complement S3 complement plus d13 S0 S1 S2 complement S3 plus d14 S0 S1 S2 S3 complement plus d15 S0 S1 S2 complement S3. The circuit diagram can be drawn as you see here. You may find it a little complicated as we have more number of AND gates. Similar to an 8 by 1 multiplexer, we can implement 16 by multiplexer using lower order multiplexers such as 8 to 1, 4 to 1 and 2 to 1 multiplexers. The figure shows the block diagram of a 16 to 1 multiplexer implemented using 2 8 by 1 multiplexers and 1 2 by 1 multiplexer. Further, we can implement the individual 8 by 1 multiplexers using 2 4 by 1 multiplexers and 1 2 by 1 multiplexer. Now, I am going to discuss the Boolean function implementation using a multiplexer. Boolean function implementation using a multiplexer. How to implement a Boolean function of n plus 1 variables using a multiplexer? To implement this, we take n variables as select lines. The remaining one variable, preferably the variable positioned at MSB, act as the input of the multiplexer. If this variable is A, then the inputs of the multiplexer will be A complement 1 and 0. These 4 lines are used together with the selection lines to generate any function of n plus 1 variables with a 2 raised to n to 1 multiplexer. Let me present you briefly the general procedure for implementing a Boolean function. First of all, we have to express the function in sum of min terms. For example, consider the function f of ABC equal to summation 1356. It is a 3 variable function where variable A is positioned at MSB. So, let us take the variables B and C as select lines. Then A is the variable remaining that is used for input. When you list out all the min terms of a 3 variable function, you can see that for the first 4 min terms 0 to 3, the value of A is 0 or in complemented form. And for the next half, that is from 4 to 7, the value of A is 1. Okay. What is next? We have to write the implementation table. For that, we list out the input labels of the multiplexer in the first row as the heading row. So, write D0, D1, D2, D3. The first column is filled with the single input variable in complemented and uncomplemented form, that is A complement and A. Then, write all min terms in 2 rows corresponding to A complement and A values. Then, circle each min term that exists in the given Boolean function. In this example, the min terms are 1, 3, 5 and 6. So, they are encircled. The next step is to find the multiplexer input values. To assign the multiplexer input value, we will follow the rules given here. The first one, when the two minterms in a column are not circled, apply a 0 value. If the two minterms in a column are circled, the input value is 1. The bottom minterm is circled, then the input value is A, and if the top minterm is only the circled one, then the input value is a complement. Now, we can write the truth table as when ABC is 0, 0, 0, F is 0, ABC is 0, 0, 1, F is 1, ABC is 0, 1, 0, F is 0, etc. ABC is 1, 1, 0, F is 1, and at last when ABC is 1, 1, 1, F is 0. And the implementation can be done as shown in this diagram. The 4 data inputs D0, D1, D2 and D3 are 0, 1, A and A complement respectively. The select lines S1 and S0 are B and C. Application of multiplexers. Multiplexer is a very useful digital circuit that has a multitude of applications. It is extensively used in data routing applications to route the data to a one particular destination from one of several sources. It is also used for the display in multi-digit BCD counters. Another application is parallel to serial conversion. In most of the digital systems, data is processed in parallel for achieving higher speeds. But for transmission of data signals over long distances, we need more number of lines. In such cases, parallel data is converted into serial form using multiplexers. The multiplexer circuits are largely used also in communication system, telephone network, computer memory and in several other applications. Let me summarize. The different types of commonly used multiplexers like 2 to 1 mux, 4 to 1 mux, 8 to 1 mux and 16 to 1 mux were explained with their Boolean expressions and logic circuits. A couple of important applications including Boolean function implementation were discussed here. Let us explore on demultiplexers in the next class. Thank you for watching. See you in the next session. Bye.